Okay, here we are, quiz 3. Something of a disaster. Well, maybe that's an exaggeration. Anyway, you should redo this. There's a number of lessons to be learned. Nothing wrong with making mistakes and learning from our mistakes, teacher and student alike. So I want you to pause the video and read over the quiz and draw the figure, the spheres, distribution of charge, and the field lines. And when you're done with that, turn the video back on. Okay, so here's the charge arrangement. And how do you come up with this? Well, you start in the middle. You know there's 8 charges in the middle and they're evenly distributed. So I draw the picture that way. Now 8 positive charges have to have 8 or 16 or some proportional number of field lines. So I'll put 8 field lines, 1 for each charge. Those field lines cannot go through the conductor. So when they go to the conductor, let me do this in black. So when they go to the conductor, they have to terminate. Because if they went into the conductor, then an electron in the conductor would move to the surface. So it can't happen. It can't go through the conductor. That's an essential feature of conductors in static equilibrium. You must know that. So that means we put in 8 lines leaving, 8 lines terminating at the surface and not going through the surface. And in order for them to terminate, there has to be 8 negative charges. Where do the negative charges come from? They come from the free electrons in the conductor. So 8 electrons come in, that leaves 8 positive charges in the conductor. But they can't stay in the conductor. Why? Because there can't be an electric field in the conductor. Why? Because if there's an electric field or a charge in the conductor, charges are going to move, and it's not in static equilibrium. These are the essential features of conductors in static equilibrium that you have to learn. So because 8 negative charges came in, and there is a positive 12 charges on that shell, then the extra 8 electrons have to go to the outside surface, and the field lines coming from those go off. I'm going to pause the video and draw this. Okay, so there's the 20 field lines going out, and it makes sense. Think about it. If you look at this field here, inside this circle that I'm drawing are 12 and 8 charges, a total of 20 charges. So these 8 terminate on the negative charges. There's now 20 charges on the outside, and so the field out here looks like the field due to 20-point charges at the center of the sphere. And we have 8 plus 12, that's the 20 charges. Okay, it all makes sense. Now, we need to calculate the electric field. We calculate the electric field for spherical charge arrangements, treating the arrangement as a point charge. But the key feature that you must remember is only the charge inside the place that you're calculating the field contributes to the field. Only Q inside. That's Gauss's law. The flux through any surface depends only on the field inside divided by epsilon naught. And so we have 4 points, well 5, 4. 0 centimeters, 4 centimeters, 10 centimeters, and 20 centimeters. So let me put those points in. This is 8 centimeters, so we're halfway out So there's the 4 centimeter point. There's the center point. Here's the 10 centimeter point. And here's the 20 centimeter point. So we want to know the field here, 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 and here. And the field at each of those points will depend on, you can use simply the equation for the electric field due to a point charge to calculate this, where r is going to be the distance to the center and q is going to be the q inside the sphere that goes through the point that you're calculating. So notice, when we do the middle, there's no charge inside. Of course, we can also look at the symmetry of the problem and guess that the electric field goes to 0. But let me just put the in here. But if we're thinking about this Q inside, we know that if we look at this point, there's no charge inside. If we look at this point, how much charge is inside? Well, it's the charge that's inside this sphere that has a radius of 4. Okay, well, we talked about this in class and most of you forgot. If this sphere here is only, remember this is a sphere, it's not a circle and it's not a line, it's a sphere. This sphere has only 1/8 the volume of this. So if the charge in this is 8 nanocoulombs, the charge in here is only 1 nanocoulomb. Now when we get out here, the charge inside is the 8. And when we get out here, at this point, the charge inside this point, or the sphere that goes through that point, are 20 charges. So that's how we calculate the field using this equation. Let's go to the next page. So we get the figure right. We drew in the field lines, and we thought through what we need to do to calculate the charge. Now, here's something that most of you have gotten sloppy about. When you do the problem, you write out the equation, each and every one. On a quiz like this, you should start with E0 and you should write it. This is what you should be writing. In fact, here, let me stop the video. You go and you write out those 4 equations, write them out in symbolic form, put the numbers in, and do the calculation. And I want you to do it for all 4 points and then come back to the video. Okay, you're back. I hope you've done it, and I hope this is what you've written. Now watch what I do and look at what you did. And if you didn't do it, shut the video off and go back and do it. Okay? So, E0. That's pretty clear what I'm doing. I'm doing electric field at the 0 point. If you don't like that, you could write ER equals 0. So what is it? It's K, Q0, R0 squared. Well, you're going to have a problem here. The Q0 is 0, but the R0 is 0, and you're dividing by 0. So we can't really do this calculation, strictly speaking, but we know that the electric field in there is 0. We'll go to E4. That's the electric field at 4 centimeters. Same equation. K, Q4 over R4 squared. Okay, now let's put the numbers in. Watch this. This is, of course you need to practice this. You're not going to just do this on the quiz, but by now you should have done it. K is 9. Forget about the 8.99. Just put 9 times 10 to the 9th. I want to see the units. The Q is what? The Q at 4 centimeters, we said it's 1 nanocoulomb. So 1 times 10 to the minus 9 coulombs over, you can't put centimeters in there. It's not going to cancel the meters. You're all putting, so many of you are putting centimeters in. You got to put meters in. So it's 0.04 meters squared, or I'm going to write it 4 times 10 to the minus 2 meters whole quantity squared. Okay, now watch. This is meters squared. Takes care of that. This is coulombs. Take care of one of those. We're left with newtons per coulomb. 9 times 1, you can do that, divided by 4 squared. Okay, what is it, 5.625? Doesn't matter, right? 9/16. This is 10 to the minus 2 squared. That's 1 over 10 to the minus 4, so that's 10 to the 4. Times 10 to the 4th newtons per coulomb. So this is what you should have written, all of this, so I can read it, and so it's well organized. So if you didn't get this, then pause the video and do the E10 and the E20 and then come back. Okay, check your work. E10, I wrote the equation. Notice the format, what you're calculating, the equation you're using, and the numbers with the units, showing all the cancellations. 9 times 8, 72. I think you can do that. 0.1, or 10 to the minus 1 squared, that's 10 to the minus 2. In the denominator, that's 10 to the 2. So 72 times 100, or 7200 is the answer. Notice the units, newtons per coulomb. Similarly for the E20, the 10 to the minus, I forgot to do that, the 10 to the 9th, 10 to the minus 9 cancel. You have 9 times 20, that's 180, over 0.2 squared, that's 0.04, or 180 over 4, you can do that. Divide by 2, 90, divide by 2 again, 45. 45, this is squared, times 100, so 4,500. Again, see the units, so I didn't do all the cancellations, I should show that. Cancellation. There's a coulomb that I didn't cancel, and there's the answer. Let's go to the final page. So take a look at this. This is those answers written out in equation editor. I didn't do the E0, I just said E0. Whoops. Wrong. The E0, I just said that. E4. There's the equation. There's all the numbers. See the units cancellation. There's the answer. Calculate it out. Same thing as we showed before for E10 and E5. And the last question was the flux. So seeing that the flux leaving the surface is going to be the same as, so you could do this, some of you tried to do this flux by calculating the field at 16 centimeters and the area at 16 centimeters. You knew to do that, but you see what I'm doing? Since I already have the field at 20 centimeters, I can just calculate the field that goes through a sphere at 20 centimeters. I will get the same result. And notice the number in the units, the A, 4 pi r squared, and I didn't write the cosine of theta because they're both, the area and the field are going out, so it's the cosine of 0. And even this calculation, if you didn't have a calculator, you would multiply the 4 times the 4,500. That would give you 1800, and then you would multiply by 0.2. Okay, well, maybe this is a little harder. But anyway, the 18 times the 2 squared is 4. That's 720. You just get the power of 10 right, and you leave the pi there. If you have a calculator, that's the result you get. If I did it, and the other way that some of you thought of, which is perfectly valid, you do this. So the flux is going to be this 20 units of charge inside. That's epsilon naught. It was on your equation sheet. And so you could just leave the number in that form, and you'd be done. If you have a calculator, you calculate it out like that. Okay, so the physics, the formatting, the numbers, the units cancellation. Pay attention to all of this, and you'll be good on the next quiz.